Alternating current systems began commercially in the United States in 1886. The outstanding advantage of the AC system is the relative ease with which alternating voltages can be generated and transformed in magnitude. At present, most of the electrical energy consumed in the United States is generated, transmitted, and utilized in the form of alternating current. In the normal AC power distribution system, the AC voltage is developed by large AC generators or dynamos, which are driven by water power, steam, or nuclear power. The output voltage from these generators is quite high, about 13,800 volts or greater. If the electrical energy were transmitted at this voltage, the line loss from the power lines would be very high due to the larger amount of power being delivered. For this reason, this high AC voltage is fed into large transformers to be boosted to an even greater value. These large transformers will boost the 13,800 volts upwards to 150,000 volts or even greater. This high AC voltage is then transmitted over the high-tension transmission lines for distances ranging up to several hundreds of miles. At 150,000 volts, the current will be low for a given amount of power, so the line losses will be low. Of course, this extremely high voltage cannot be used safely in homes, so it must be lowered to some safer value, usually 120 volts, before it is brought into the homes of the consumers. This task is also performed by transformers. As you will see, transformers can be used to change low-value AC voltages into high-value AC voltages and vice versa, and it is done very efficiently. For this reason, the transformer costs very little to operate. Transformers, however, cannot be used with DC voltages, and no other means of transforming low values of DC into high-value DC voltages in an efficient manner have been developed. For this reason, alternating current is used almost exclusively, as was mentioned earlier. In Part 4 of the Ucando video series, you will learn that we must change the AC voltage from the power lines into a DC voltage for operation of electronic circuits. This is performed by circuits known as rectifier circuits, which are the heart of the power supply system. You will also learn that when we apply this DC voltage to certain types of transistors or integrated circuits or other types of semiconductor devices, these circuits will generate an AC voltage. This type of circuit is called an oscillator. You will learn more about oscillators in Part 6 of this series. What is AC? By definition, AC stands for alternating current. AC is a current that periodically changes in magnitude and direction. Here we see a diagram of a circuit that can be used to produce an alternating current. When the switch is in position 1, the electrons will flow from the negative side of the battery through the switch and into the resistor at point A. Next, the current will flow through the resistor to point B and then return to the positive side of the battery. When the switch is thrown from position 1 to position 2, the current will flow from the negative side of the battery into the resistor at point B, through the resistor to point A, then through the switch and back to the positive side of the battery. If we continue throwing the switch from position 1 to position 2 and then from 2 to 1 at 1 second intervals, there will be an alternating voltage across the load resistor. The current flows through the load resistor and will be reversing itself at 1 second intervals. The AC circuit we have just described is a very simple one, and the AC voltage, which is generated commercially, is considerably different. The most common type of AC wave and the type most practical to generate is called a sine wave. Here we see a graph of a sine wave. The voltage is plotted on a vertical axis and the time in seconds is plotted on a horizontal axis. As you see, the voltage is changing in both magnitude and direction, so it fits the definition of alternating current. Let's examine this graph of the AC voltage. At 0 time, the voltage is 0. At 1/240th of a second later, the voltage has increased to its maximum peak potential. The voltage gradually decreases until at 1/120th of a second, the voltage has again reached 0. Now the voltage begins to build in a negative direction. At 1/180th of a second, the voltage has reached its maximum negative peak potential. In the time span from 1/80th to 1/60th of a second, the voltage decreases to 0 volts again. This is one cycle of the AC voltage. By definition, a cycle is one complete succession of events. We notice that the voltage started at one value, went through all the variations, then returned to its original value to complete one cycle. Notice that each cycle occurred in 1/60th of a second. This AC voltage is also called the 60-cycle AC voltage. Another term which is used in connection with AC is alternation. An alternation is 1/2 of an AC cycle. On the graph of the sine wave, that portion of the sine wave from 0 to 1/120th of a second is one alternation, and the portion of the sine wave from 1/120th of a second to 1/60th of a second is the second alternation which occurs in the sine wave cycle. Another term which is used in conjunction with AC voltages is frequency. Frequency is the number of times anything happens in a given time period. When applied to AC voltage, the frequency represents the number of cycles which occurs in 1 second. The frequency of the wave shown here would be 60 cycles per second, or 60 hertz. The AC voltages supplied to most homes in the United States have a frequency of 60 cycles per second. The frequency of an AC voltage is very important. Frequencies above 150,000 cycles per second are called radio frequencies. Radio frequency signals will range from thousands to millions of cycles per second. The terms K, M, and G are used to designate thousands of cycles per second, millions of cycles per second, and thousands of millions of cycles per second. You will see these three terms used a lot when dealing with radio frequency signals. In 1966, a new term was adopted to represent cycles per second. The term is Hertz. It was used to honor one of the early experimenters in radio, Heinrich Hertz. Thus the term which we used before for 60 cycles per second, which was 60 Hertz. The written abbreviation for Hertz is Hz. The period of the wave is defined as the time required for one cycle to occur. If the frequency of a wave is 60 Hertz, then each individual cycle would last for a period of 1/60th of a second. The period of a frequency is measured in time. To calculate for the period of a signal, you divide the frequency of the signal into 1, or T equals 1 over F. In this formula, T represents the period in seconds, F represents the frequency in cycles per second, or Hertz. In your studies of direct current, you learn that voltage caused the current to flow through the circuit. This also holds true for alternating current circuits. Electrons flowing through a resistor generate heat regardless of whether they flow steadily in one direction or reverse their direction periodically. When AC current flows through the filament in a light bulb, the filament will illuminate. If the frequency of the AC is above 30 Hertz, the bulb will appear to be giving off a steady light. Actually, the filament cools off somewhat as the alternating current goes through zero, but the eye does not detect this. Here we see a graph of an AC voltage being applied across a resistor. We have plotted both the voltage and the current. Notice the points where the voltage passes through zero are the same points where the current passes through zero. Also notice that the voltage and current reach their peak values at the same time. This is true for a circuit containing resistance, but it is not true if the circuit contains a coil or a capacitor or both. We shall learn more about coils and capacitors later. When the two curves coincide as they do in our graph, they are said to be in phase. When they do not coincide, they are said to be out of phase. Here we see another graph of a sine wave, but this time the time axis is marked off in degrees instead of seconds. This is possible because a cycle represents one complete succession of events. Therefore, the cycle of an AC wave may be broken into degrees. There are 360 degrees to one cycle. A cycle may be further broken down into quadrants of 90 degrees each. Notice at 0 degrees and 180 degrees, the voltage of the sine wave is 0, and at 90 degrees and 270 degrees, the voltage of the sine wave is at its peak value. The peak value of the sine wave is the greatest value to which the voltage or current will rise. If lines are placed on the graph that intersect the sine wave curve, Each of these lines will have a different length and will represent the voltage at some particular point in time. The voltage at this instant in time is known as the instantaneous voltage of the waveform. From this graph, it is evident that the instantaneous voltage from a sine wave depends on the particular instant at which the voltage is measured. By referring to this table, you can find the value of a sine wave at any instant of time. For example, if the peak value of a sine wave is 100 volts, what is the value of the voltage at 20 degrees? By looking at this table, we see the sine of 20 degrees is 0.34. Therefore, if we multiply 0.34 times 100, we see that the instantaneous voltage at 20 degrees is 34 volts. At 140 degrees, the sine is 0.643, so the instantaneous voltage at 140 degrees is 64.3 volts. And at 240 degrees, the sine is minus 0.866, so the instantaneous voltage at 240 degrees is minus 86.6 volts. Another term used in conjunction with the sine wave is the average value. The average value of the sine wave is the average height of the curve for one alternation of the sine wave. Remember, one alternation is only half a cycle. The average height of a sine wave is found to be 0.637 or 63.7% of the peak value. Therefore, to find the average value of a sine wave, you would multiply 0.637 times the peak value. If you know the average value of a sine wave, you must know the peak value, then you would divide 0.637 into the average voltage value. The average value of the AC wave is seldom used in the technician's line of work. Most of the time, voltage and current are specified in their effective value. The effective value of a sine wave is defined as that value which will produce the same heating effect in a resistor as would be produced by a given value of a direct current or voltage. The effective value of the sine wave can be thought of as the working value of the sine wave. The effective value of the sine wave is 0.707 times the peak value. If you know the effective value of a wave and you need to calculate for the peak value, you simply multiply the effective value times 1.414. The 120 volts in your home is actually a sine wave voltage with an effective value of 120 volts. The peak value of this voltage is actually 169.68 volts. All AC voltmeters and current meters will read effective values unless otherwise stated. When we speak of an AC voltage or current, we mean its effective value. The wavelength of an AC sine wave is the actual physical length of one cycle in space. Wavelength is equal to the speed at which electric waves travel through space, divided by the frequencies in cycles per second. The electric wave will travel at the speed of light, which is approximately 186,000 miles per second, or 300 million meters per second. To calculate the wavelength of a wave in meters, you divide 300 million by the frequency in cycles. Stated mathematically, 300 times 10 to the 6th power divided by frequency equals a wavelength in meters, and 186,000 divided by frequency equals a wavelength in miles. The symbol for wavelength is the Greek letter lambda. For example, suppose we wish to find the wavelength of a radio station which operates on a carrier frequency of 1,000 kilohertz. Using the formula wavelength equals 300 times 10 to the 6th power divided by the frequency, we learn the actual length of one cycle in space of this radio wave is 300 meters long. The wavelength of a TV station operating at 100 megahertz would be 300 times 10 to the 6th power over 100 times 10 to the 6th power, or 3 meters. The wavelength of a 60-cycle power line would be 300 times 10 to the 6th power divided by 60, or 5 million meters. As you have seen, the lower the frequency, the longer the wavelength. The higher the frequency, the shorter the wavelength. Alternating currents are more complex than our direct currents. Therefore, more factors must be considered. One factor which makes the study of AC more complex is the matter of phase. Phase is a measure of time. It shows how one sine wave varies with respect to another sine wave of the same frequency. As we saw earlier, when two or more sine waves, either current or voltages, or both, are in the same phase, they pass through corresponding values at the same time. In other words, they both pass through zero at the same time, and they both reach their peak values at the same time. This continues to happen during each cycle. Here we see two sine waves which are 90 degrees out of phase. Notice that one sine wave has reached its peak value as the other sine wave is just crossing its zero voltage point. When we look at the waveform, we see that one sine wave started 90 degrees before the other sine wave. We could say that one sine wave is leading the other sine wave by 90 degrees, or we could state that one sine wave is lagging the other sine wave by 90 degrees. Either would be a correct statement. Here we see two sine waves which are 180 degrees out of phase. These two waves will go through their zero values at the same instant, but one is increasing in a positive direction while the other is increasing in a negative direction. Before continuing and learning more about alternating current, let's review some of the material covered to this point. You have seen that one cycle is one complete succession of events. You learned that the sine wave started at one value, went through all the variations, and returned to its original value. You also learned that the time required for one cycle to occur is called the period of a wave. The period will consist of two alternations, one swinging positive and the other swinging negative. You saw that a sine wave has a peak value, an effective value, and an average value. The effective value is 0.707 of the peak value and can be thought of as the working value of the sine wave. All meters will read in effective values unless they indicate otherwise. The wavelength of a signal is the actual physical length of one cycle in space. The wavelength can be calculated in meters or miles. The higher the frequency, the shorter the wavelength. You have also seen in a purely resistive circuit that current and voltage are in phase. We will now continue instruction in alternating current. It is now quite easy to understand that there are a wide variety of phase relationships existing between two or more sine waves. Phase relationships can range from 0 to 359 degrees out of phase. You may be wondering, under what conditions will the out-of-phase signals occur? Well, the answer to that question is an easy one. Any time a circuit with an AC voltage applied has capacitance or inductance, or both in the circuit, there will be an out-of-phase condition which will exist between the voltage and the current. Here we see an AC generator connected to a capacitor with a graph showing the voltage wave and the current waveforms. If you notice, the current is leading the voltage by 90 degrees. You will learn more about why this occurs when we discuss the capacitor. Here we see an AC generator connected across a coil. We also see a corresponding graph showing the phase relationship between the current and voltage for the coil circuit. As you can see, when an inductance is placed in a circuit, it will cause the voltage to lead the current by 90 degrees. We have already seen the phase relationship of the voltage and current in an AC circuit which contains only resistance. The current and voltage were in phase. If the circuit contains a combination of resistance, capacitance, and/or inductance, a wide variety of phase relationships may result. The amount of phase difference will be determined by the amount of reactance and resistance in the circuit. This is also called the circuit's impedance. Impedance is the total opposition that a circuit offers to the flow of alternating current at a given frequency. Impedance is measured in ohms, and its symbol is the Greek letter zeta, or Z. Impedance is equal to the square root of the resistance squared plus the reactance squared for a typical series AC circuit. Reactance, as you will learn, is the opposition that a capacitor or inductor has in an AC circuit. Reactance is measured in ohms, just like resistance and impedance. The value of reactance will depend largely on the frequency of the AC signal being applied. You have already seen that in an AC circuit containing an inductor, the voltage will lead the current by 90 degrees. In an AC circuit containing a capacitor, the current will lead the voltage by 90 degrees. Therefore, since the voltage leads the current by 90 degrees in a purely inductive circuit, and the voltage lags current by 90 degrees in a purely capacitance circuit, the effect of one of the reactances will tend to cancel the other. For example, let's assume that coil L1 has an inductive reactance of 100 ohms, and capacitor C1 has a capacitive reactance of 50 ohms. The total reactance of this circuit would be 50 ohms of inductive reactance. This was obtained by subtracting the smaller reactance from the larger. Many circuits, however, will contain inductive reactance, capacitive reactance, and also resistance. Therefore, to determine total opposition to the flow of current in the series AC circuit, you must use the impedance formula. By assigning values to the components in our circuit, we are able to determine the circuit's impedance. We start by subtracting the capacitive reactance from the inductive reactance. Next, we square the resistive value and the reactive value, then add the two sums together. Next, we take the square root of this value. We see that the impedance of this circuit is 320.2 ohms. It is important to understand, however, that this formula will not apply to parallel LC, RC, RL, or RLC circuits. To calculate for the impedance of parallel connected components in an AC circuit, you must first find the current flow and then use Ohm's law Z equals E over I. We have assigned values to the components in our circuit. To calculate the impedance of this circuit, we must first calculate the current flow through each component. We do this by using Ohm's law, I equals E over R. We see that there are 40 milliamps of current flowing through the inductive branch, 50 milliamps of current flowing through the resistive branch, and 25 milliamps of current flowing through the capacitive branch. Since the current flowing through the inductive branch and the capacitive branch are 180 degrees out of phase, we must subtract the smaller current from the larger current. This shows the total reactive current flow is 15 milliamps. Once we know the total reactive current flow and the current flow through the resistor, we use the formula square root of IR squared plus IX squared. Remember, IR squared is the current flow through the resistor, and IX squared is the reactive current flow. This will show there is a total current flow of 52.2 milliamps through the circuit. By using the formula Z equals E over I, we are able to calculate the impedance of this circuit as 192.3 ohms. Now you can see that determining the impedance of a parallel circuit involves more math functions than the simple series AC circuit. Next, we shall see how to add two AC voltages which are out of phase, but operating at the same frequency. In a DC circuit, you can easily find the resultant value of two voltages in the same circuit by simply adding them algebraically. If the voltages are of the same polarity, you simply add them together. If the voltages are bucking or opposing one another, you subtract the smaller value from the larger value. In an AC circuit, however, the simplest way to understand and work many AC circuit problems is to draw a vector diagram to scale. To accomplish this, you will need a ruler for drawing straight lines and for measuring distances, and you will also need a protractor for measuring angles. The ruler should have a centimeter scale, since centimeters are divided into tenths and are therefore much more convenient to use in these applications. To express the quantities of a sine wave, it is necessary to state their direction as well as their magnitude. This is accomplished by means of a straight line called a vector. The length of a vector will be proportional to the magnitude of the quantity. The arrow is placed at one end of the line to indicate the direction of the quantity. There are 5 rules you should remember when working with vectors. A vector may be used to represent a sine wave of voltage or current. 2. A vector can rotate one full revolution in a counterclockwise direction. 3. The length of a vector represents the amplitude of the signal. 4. A vector has direction as indicated by the arrow. And 5. The phase relationship of two sine waves may be indicated by the angle between the vectors used to represent these waves. Here we see a vector for two voltages 45 degrees out of phase. One has an instantaneous voltage of 50 volts and the other an instantaneous voltage of 30 volts. If you notice, the 30 volt vector is placed 45 degrees in a counterclockwise direction from the 50 volt vector. The simplest method of finding the result of these two vectors is to use the parallelogram method. To achieve this, first we draw a line from point A and make it parallel with the vector at point B. Next, we draw a line from point B and make it parallel with the vector at point A. Since the 30 volt vector was 45 degrees from the 50 volt vector, then this line must also be at 45 degrees. Where the two lines intersect will be called point C. Now draw a line from where the two original vectors are joined. This line becomes the resultant vector. Now you must measure the length of the resultant vector with the ruler marked in centimeters. When we do this, we learn the combination of the voltages has a net force of 74 volts. To find the phase relationship of the two signals, use the protractor and measure the angle between the resultant vector and the vector at 0 degrees, which is vector line B. We learn the phase relationship between these two voltages is 16.6 degrees. This example was used to introduce you to the subject of vectors. Other applications of vectors will be made from time to time in your training in electronics. You will find that vectors are used a great deal when explaining sine waves in AC circuits. At the beginning of our program, it was mentioned that one of the outstanding advantages of the AC sine wave was its ease with which it could be transformed in magnitude. The voltage can either be stepped up or stepped down with the use of a transformer. Transformers will usually have two or more windings. One winding is called the primary winding, and the second winding becomes the secondary winding. These windings are usually wrapped around a common core made from laminated sheets of iron. If the current flowing through the primary coil is fluctuating, then a current will be induced into the secondary coil. Transformers have the ability to transform voltage and current to higher or lower levels. Transformers cannot, of course, create power from nothing. Therefore, if a transformer steps up the voltage of a signal, it will reduce its current. In the same respect, if it steps down the voltage, then it will increase the current. As we shall see, the power flowing from a transformer cannot exceed the incoming power. We will begin our discussion of transformers with the coil. After all, a transformer is basically two coils which are electromagnetically coupled together. An important quality of a coil is its ability to oppose any change in current passing through it. This property is called inductance. When a current starts to flow through a conductor, a magnetic field will start to expand from the center of the wire. These lines of force will move outward through the conducting material itself and then continue into the air. As these lines of force are expanding, they will cut through other conductors of the same coil. This will induce a voltage into these conductors. This induced voltage will be such that it will be in a direction completely opposite of the direction of the current flow. Because of its opposing direction, it is called a counter-electromotive force. The effect of this counter-electromotive force, which builds up in the conductor, is to oppose any increase in current. At the instant the current begins to flow, the lines of force will be expanding at their greatest rate, and the greatest value of counter-EMF will be developed. If a switch in a current-carrying circuit is opened suddenly, there will no longer be any current to support the magnetic field, and it will begin to collapse back around itself. As the field collapses inward, a voltage in the opposite direction will be induced. This voltage could also be called a counter-electromotive force, but it is usually known as a self-induced voltage. This self-induced voltage will be such that its polarity will be the same as the applied source voltage. Therefore, the voltage due to self-induction tries to maintain the current flow through the circuit. As you have learned, inductance is a property of a coil which opposes any change in current. The unit of measurement of inductance is the Henry. 1 Henry is defined as the amount of inductance required to produce a counter EMF of 1 volt when an average current change of 1 ampere per second is occurring in the circuit. Inductance is represented by the letter L, and Henry is represented by the letter H. Alternating current is in a constant state of change, and the effect of the magnetic fields produced when the current flows through a coil is a continual induced voltage that opposes any change in current. This reacting ability of the inductance against the changing current is called inductive reactance. As was discussed and shown earlier, inductance is the property of a circuit which opposes any change in current and is measured in henries. Inductive reactance, on the other hand, is a measure of how much the counter-electromotive force will oppose the current variations. This opposing effect of the reactance is measured in ohms. The inductance of a coil will not change. If the coil has a value of 1 Henry, it will be 1 Henry whether it is used in a 60 Hz circuit or in a 2 MHz circuit. The inductance of a coil is dependent on its physical properties. The inductive reactance, however, depends greatly on the frequency of the signal being applied. In a 100 Hz circuit, the magnetic field builds up and collapses at a fairly low rate of speed, and a small amount of counter-electromotive force will be produced. However, as the frequency is increased, the magnetic field will move more rapidly and produce a greater amount of counter-EMF, which opposes the current even further. As you can see, the amount of inductive reactance is directly proportional to the frequency of the signal being applied. Another factor which affects the inductive reactance of a coil is its inductance. If the inductance is doubled, the inductive reactance will also double. Therefore, the inductive reactance is also directly proportional to the inductance of a coil. The formula we used to measure the inductive reactance of the coil circuits was XL equals 2 pi FL, where XL represents the inductive reactance, F represents the frequency, and L represents the inductance. The unit of measurement for inductive reactance is the ohm. If the reactive value in a circuit is at least 10 times greater than the resistance of the circuit, then you may use Ohm's law for the AC circuit, but you must substitute the reactance value for the resistance value. The formula becomes E over I times X. Also, if 2 uncoupled inductive reactants are in series, the total reactance can be calculated by adding their inductive reactance together. Mathematically stated, inductive reactance totals equal the inductive reactance of L1 plus the inductive reactance of L2. If 2 uncoupled inductive reactants are in parallel, total reactance may be calculated using the formula total inductive reactance equals the reactance of L1 times the reactance of L2 over the reactance of L1 plus the reactance of L2. By uncoupled, we mean that the flux lines from one coil does not cross into the other coil. Now that we have learned a little bit about coils and reactants, let's look at the transformer. We will start our study of transformers by looking at the power losses in a transformer. There are 3 basic power losses in a transformer. They are eddy currents, hysteresis, and copper loss. Let's first examine eddy currents. To produce a transformer that is highly efficient and has a minimum number of turns, the primary and secondary coils are wound on a core of iron or some other highly permeable material. When the transformer is in operation, an intense moving magnetic field will be produced in the core. Since iron is a fairly good electrical conductor, these magnetic fields will induce circulating currents in the core material. These circulating currents are known as eddy currents, and they can produce a considerable power loss in the form of heat in the core. To overcome this power loss, the core is made from laminated sheets that are stacked together. These laminated sheets are very thin and are coated with an insulating material such as varnish or plastic. By using the laminated sheets, the eddy current is limited to the thickness of a single sheet. This limits the length of the path and limits the amplitude of the eddy current and holds heat loss in the core to a minimum. The thinner the laminations, the less the eddy current loss. Since the eddy currents are caused by the magnetic field, the higher the frequency, the more the eddy current losses will be. The next power loss is called hysteresis. Hysteresis is due to residual magnetism within the core material. This residual magnetism requires energy from the source to realign the molecules continuously in the core material, which develops heat. The final transformer power loss we shall examine is the copper loss. As the current flows through the wires of the transformer, it causes the wires to generate heat, and the heavier the load placed on the transformer, the greater its heat will be. Most transformers are constructed of several layers of wire wound on the core material. These layers of wire create a tendency to retain heat within the wires. This increase in temperature will cause the resistance of the wire to increase, thereby creating even more of a power loss. As a result, it becomes necessary to use heavier wire to reduce the resistance and heat loss in the transformer. You will always find that more power is fed into the primary of a transformer than is delivered by the secondary to the load. This difference between the input and output power is the sum of all the power losses in the transformer caused by eddy currents, hysteresis, and copper loss. The ratio of the output power to the input power is the efficiency of the transformer. The efficiency can be determined by using the formula percent of efficiency equals the power out divided by the power in. This power ratio will always result in a decimal number less than 1. Before proceeding into the next part of the program, let's review the information just discussed. As you have seen, AC voltages are not always in phase. Therefore, to calculate the total voltage of two out-of-phase signals, you must use the parallelogram method of vectoring. You have seen that reactance is the opposition that a coil has in an AC circuit, and the reactance is measured in ohms. The formula for inductive reactance is 2 pi equals the frequency times the coil's inductance in henries. Anytime you have a circuit which contains both reactance and resistance, the impedance of the circuit must be calculated. The impedance is the total resistance offered to the circuit's total current flow. To calculate the impedance of parallel connected components, you must first find the current flow through each parallel branch. Next, use the formula, the square root of the resistant current flow squared plus the reactive current flow squared. Remember, if a coil and a capacitor are both being used in the circuit, you must subtract the smaller reactive value from the larger reactive value. After you have determined the total current flow in the circuit, you use the formula impedance equals the voltage divided by the current. To calculate the total reactance for two uncoupled coils in series, you simply add their values together. To calculate the total reactance of two uncoupled coils in parallel, you must use the formula inductive reactance of L1 times the inductive reactance of L2 divided by the inductive reactance of L1 plus the inductive reactance of L2. All transformers have power losses which result in a decrease in the transformer's efficiency. To calculate the efficiency of a transformer, you must use the formula power out divided by power in. This number will always be less than 1 and will be indicated as a percentage. Transformer power losses are caused by one of three things: eddy currents, hysteresis, or copper loss. Eddy currents are losses induced by circulating currents within the core of the transformer. To overcome this loss, the core is made from thin laminated sheets of iron or steel, which are coated with an insulating material such as plastic, then stacked together. Hysteresis is the result of the molecules within the core material continuously being realigned by the magnetic field. Copper loss results from the resistance of the copper wire used in the windings. The smaller the wire used, the higher the copper loss will be. And in the same respect, the heavier the load, the higher the copper loss will be. This concludes review number 2. Now to continue with AC. In this part of the program, you will learn about the various types of capacitors. Capacitive reactance is explained as our capacitors in series and in parallel, phase relationship, and color codes. Basically, a capacitor has the ability to hold a charge of electrons. The number of electrons it can store under a given voltage is a measure of its capacitance. Two separate metallic plates with a non-conducting material sandwiched between them forms a simple capacitor. The capacitance of a capacitor is dependent on the physical characteristics of the capacitor. These characteristics are first the plate area, second the plate separation, third the number of plates, and fourth the nature of the dielectric material. Let's take a look at dielectric material. For a given charge on a capacitor, the voltage across the capacitor can be changed by changing the dielectric material between the plates. For example, if we take a capacitor with an air dielectric and charge it with a power source to 20 volts, then remove it from the power source, it will retain the 20-volt charge. Now suppose we insert Teflon between the plates. The Teflon will weaken the electric field between the two plates. Since the voltage across depends on the strength of the electric field, the weakening of the field means the voltage across the plates will go down. Even though the voltage across the plates has decreased, there is still no complete path for the electrons to flow through, so the same number of electrons must still be on the negative plate. The amount of charge on the capacitor will remain the same. By putting the Teflon dielectric between the plates, we have doubled the capacitance of the capacitor. The ability of the dielectric to increase capacitance is called the dielectric constant. As you can see, Teflon has a dielectric constant of 2. Therefore, when Teflon is used as the dielectric material, it will double the chargeability for the same voltage across the plates. In effect, it doubles the capacitance of the capacitor. Air is arbitrarily assigned a dielectric constant of 1. All solid substances and liquids will have a dielectric constant greater than 1. As you should recall, the current through an inductor will rise slowly to its final peak value. There is a similar situation in a capacitor, except that it is the voltage across the capacitor which rises slowly to its peak value. When a capacitor is first placed across a power source, the voltage across the capacitor will not equal the source. Instead, it must charge up to the potential of the source. It will charge rapidly at first, then as the electrons build up on the plates of the capacitor, it produces a counter-electromotive force that will oppose the source of the voltage. When the capacitor voltage reaches the voltage potential of the source, the current flow through the capacitor will cease. This is because the voltage across the capacitor will buck the source voltage, and therefore will be no difference of potential, and hence no current will flow through it. Another way to change the capacitance of a capacitor is to increase the plate separation. If the spacing between the plates is doubled, the capacitance will only have half the value. This is true because the path for the electrostatic lines of force between the negative plate and the positive plate is now twice as great, which results in only half as intense an electrostatic field and thus only half as much capacitance. In other words, capacitance is inversely proportional to the spacing between the plates. Even though increasing the space between the plates of a capacitor decreases its capacitance, it does increase the voltage rating of the capacitor. Another factor which affects the capacitance of a capacitor is the number of plates. A 3-plate capacitor will have twice the plate area exposed as a 2-plate capacitor, therefore twice the capacitance. A 4-plate capacitor will have 3 times the capacitance. Multi-plate capacitors are usually designed so the plates are stacked on top of one another, separated by strips of dielectric material. The plate area of the capacitor is another factor affecting the capacitance. If the plate area is doubled, the capacitance will double. Many times, capacitors are placed in parallel to increase the capacitance in a given part of a circuit. This has the same effect as increasing the plate of a capacitor. The formula for computing the capacitance of 2 or more capacitors in parallel is simply capacitance total equals C1 plus C2 plus C3 and so on. When connecting capacitors in parallel, care must be given to assure that their working voltage ratings are similar. The reason for this is the highest voltage the parallel combination will stand will be determined by the capacitor with the lowest voltage rating. When two capacitors are connected in series, the equivalent capacitance of the two will be less than that of either capacitor by itself. This is due to the fact when capacitors are connected in series has the same effect as increasing plate separation. Remember, when plate separation is increased, capacitance is decreased. Capacitors are sometimes placed in series so they can be used across a higher voltage than that for which they were designed. By placing the capacitors in series, it increases the thickness of the dielectric, which in turn increases the voltage rating. Therefore, it takes more voltage to puncture the thicker material. The voltage rating will be determined by the sum of the rating for each capacitor in the series combination. Here we see two useful formulas for calculating the equivalent capacitance of capacitors in series. CE equals C1 times C2 over C1 plus C2, or CE equals the reciprocal of C1 plus the reciprocal of C2 plus the reciprocal of C3 divided into 1. Notice the similarity between these two formulas and those used for resistors in parallel. The value of the voltage drop across a particular capacitor in a series group will be inversely proportional to the ratio of its capacitance to the total capacitance. The trouble with connecting capacitors in series so they can be used at a higher voltage is that capacitance is reduced. As a result, the capacitance may not be enough to do the job. This problem can be overcome by connecting in parallel as many series strings as are needed to provide sufficient capacitance. The dielectric materials used in a capacitor are not perfect insulators and will pass a slight amount of DC current called leakage current. The amount of leakage that a capacitor has is apt to be different in two supposedly identical capacitors. Leakage will also vary with the capacitor's age and climatic conditions. Electrons on the negative plate of a charged capacitor may find a high resistance path to the positive plate either through the dielectric material or over the surface of the capacitor. It will leak from one plate to the other. Therefore, leakage current is a loss to a capacitor. When this leakage current has increased sufficiently, it will cause the capacitor to operate warm, due to the energy being lost in the form of heat. Another loss in a capacitor is due to hysteresis. This can also be indicated by heat in a capacitor. Hysteresis loss in a capacitor is caused by the friction of the molecules of the dielectric material as they are changed from one polarized position to another due to the reversing electrostatic lines of force between the plates. The hysteresis loss in a capacitor will increase as the frequency of the AC signal increases. How effective a capacitor is in allowing AC to flow depends upon its capacitance and the frequency being applied across it. The greater its capacitance, the more electrons will be required to charge the capacitor to the source voltage potential. The actual resistance effect of a capacitor is known as its capacitive reactance, which is measured in ohms. To calculate for the capacitive reactance of a capacitor, use the formula XC equals 2 pi times the frequency times capacitance divided into 1. The reactance of a capacitor will be inversely proportional to the frequency. As the frequency is increased, the reactance of the capacitor will decrease. At high frequencies, the charging and discharging of the capacitor takes place very rapidly, and the capacitor will pass a large current. In an AC circuit containing a series pass capacitor, the current and voltage may be 90 degrees out of phase. The current will lead the voltage by 90 degrees. The reason for this is because when the voltage is first applied to the capacitor, it will conduct a heavy current flow, but the voltage must take time to charge to its full potential. Also, when the charged capacitor is discharged, it will conduct another heavy current flow immediately, but the voltage will not drop as rapidly because it must take time to discharge. For this reason, a phase shift exists between the voltage and current of the capacitor. The only time there will be a 90-degree phase shift is if there is no resistance in the circuit. When resistance is present in the circuit, the difference in phase will be less than 90 degrees. The phase difference will continue to decrease as the resistance in the circuit is increased. If the resistance of the circuit is 10 times or more larger than the capacitive reactance in the circuit, the phase shift will approach zero. Some capacitors, like the resistor, use a color code to identify their capacitance. Other capacitors have their working voltage and capacitance printed on them. The color code for capacitors is the same code used for resistors. The simplest code is a 3-dot code used with 500-volt mica capacitors. These capacitors have a tolerance of 20%. The first dot represents the first digit, the second dot represents the second digit of the value, and the third dot indicates the multiplier. The 6-dot code reads clockwise, starting with the left dot. The first dot is usually white. This indicates it uses the Electronic Industries Association code, or EIA for short. The second dot represents the first digit of the number. The third dot represents the second digit of the number. The dot below the second digit represents the multiplier. The next dot to the left represents the tolerance. The last dot represents the temperature coefficient. The temperature coefficient is the degree by which the capacitor will change its capacitance with a change in temperature. Now that we know the basics about a capacitor, let's see how they operate in a circuit. To do this, we will use a system containing a pump, a water wheel, a shutoff valve, and a cylinder containing a spring. The pump will represent a power source. The water wheel will represent the load. The shutoff valve is the controlling device, such as a transistor, and the cylinder represents a capacitor. When the pump turns on, it forces the water through the valve and into the left side of the cylinder. As the water fills the cylinder, it causes the water on the right side of the cylinder to flow out through the water wheel. When this happens, the water wheel turns. The water flows through the water wheel and back to the other side of the pump. This will continue until the water pressure in the cylinder becomes equal to the pressure being produced by the pump. Once the cylinder becomes pressurized by the pressure from the pump, the shutoff valve closes and the pump is turned off. This will then cause the cylinder to hold the water pressure. When this happens, the compressed spring in the cylinder will equalize itself and return to its neutral position. As the piston in the cylinder is returning back to its midpoint, its water will flow from the left side to the cylinder, back through the valve and pump, and into the water wheel. This causes the water wheel to rotate in the opposite direction. The water appears to continue to flow through the cylinder. This will continue until the pressure in the cylinder on both sides of the piston becomes equal. Now, let's suppose the pump can be continually turned on and off. As it is, the cylinder will continually become pressurized by the pump, then equalize when the pump shuts off. As you can see, the water wheel will continue to alternate first in one direction, then in the other. As you noticed, even though no water actually flows through the cylinder, the water wheel continued to alternate directions with the flow of water. We shall now use the same idea and apply it to a capacitor circuit. In this circuit, we have replaced the pump and shutoff valve with an AC generator. We have replaced the water wheel with a resistor and the cylinder with a capacitor. We've also placed an amp meter in series with the load to monitor the current flow. As the AC signal rises to its positive peak, the capacitor starts to charge to the peak value of the AC generator. As the capacitor is charging, the amp meter indicates a current flow in the positive direction. Therefore, we have a current flow through the load resistor and through the amp meter. As the signal starts back down from its positive peak, the capacitor will not immediately equalize and discharge through the load resistor. When the AC signal has reached its zero reference point, the amp meter will begin to decrease back to the midpoint. Next, the sine wave starts in the negative direction toward its most negative peak value. As it does, the amp meter starts to swing to the negative reading, indicating a current flow in the opposite direction. The capacitor will also be charging in this direction. After the sine wave has reached its most negative peak value and the capacitor has become charged, the sine wave starts back toward the zero reference line to start the process all over again. As the AC sine wave continues to alternate first in one direction and then in the other, the capacitor will continually charge and discharge through the load of the circuit. As you have seen, the load resistor sees a current flow first in one direction, then the other. As far as the load resistor is concerned, the alternating current is flowing through the capacitor, even though no electrons actually pass through the dielectric. There are a wide variety of capacitors used in today's modern circuits. We will briefly cover 7 of the most common types. The first type uses an air dielectric. It has very little leakage and is made in fixed and variable sizes. These capacitors are used in both low and high voltage applications. You will find this type of capacitor in transmitters and receivers. They are available in a wide range of capacitive values, but they are rarely larger than 400 picofarad. The air dielectric cap is used in frequencies up to 1000 megahertz. Therefore, they are used as tuning elements in receivers and transmitters. This is a mica capacitor. It also has very low leakage and is available in fixed and variable sizes. The working voltage of the mica capacitor will range from about 350 to several thousands of volts. The capacitive value of this capacitor is generally between 1.5 picofarad to 0.1 microfarad. These capacitors are used in RF circuits and will operate at frequencies up to about 300 megahertz. The mica capacitor finds general use as RF bypass capacitors. Here is a ceramic capacitor. The ceramic capacitor has low leakage and is also available in both fixed and variable sizes. The capacitive values will range from 1.5 picofarad to about 0.01 microfarad. The working voltage of the ceramic capacitor is about 500 volts and will operate at frequencies up to 10,000 megahertz. The ceramic cap is used as a general purpose capacitor. This is a paper capacitor. It has fairly low leakage when new, but has a tendency to form moisture inside, which causes the leakage to become very high. It is available in sizes ranging from 10 picofarad to about 10 microfarad. The working voltage of this capacitor will range from 100 volts to several thousand volts. These capacitors are used in frequencies from 100 hertz to 1 megahertz. This capacitor is plastic and has very low leakage. It is used in frequencies ranging from DC to 10 megahertz. The plastic capacitor is available in sizes ranging from a few picofarad to up to a few microfarad. The working voltage of this capacitor is good to several thousand volts. The plastic capacitor is used to replace the paper capacitor in many applications. This is a tantalum capacitor. This capacitor has very low leakage and is used in frequency applications ranging from DC to 1 kilohertz. The size of this capacitor will range from 100 picofarad to several hundred microfarad. The working voltage of this capacitor is only about 300 volts. These capacitors are used in direct current circuits only. Here we see an electrolytic capacitor. The electrolytic capacitor has considerable leakage, especially when used at voltages over its rated value. These capacitors will range from a few microfarad to over 50,000 microfarad. The working voltage will range from 6 volts to about 700 volts. These are normally polarized and should never be connected in a circuit backwards. If a polarized electrolytic is connected across a circuit with reversed polarity, the capacitor will become a good conductor. This will cause a high current flow, which develops heat in the capacitor. The heat will cause the electrolyte to boil, and the capacitor may explode. Therefore, the electrolytic capacitor cannot be used in an AC circuit. The electrolytic capacitors are commonly used as power supply filters and as coupling capacitors in transistor circuits. We are now ready for the final review in the AC video. You have seen that the capacitance of a capacitor depends on 4 physical characteristics. These are the type of dielectric materials used, the plate separation, the number of plates, and plate area. You have also seen that the capacitive reactance of the capacitor depends on the capacitance of the capacitor, as well as the frequency of the signal being applied. Some capacitors are also color-coded using either the 3-dot or the 6-dot system. The colors in the color code are the same ones used for the resistor color code. Capacitors also have losses. The 2 most common are leakage and hysteresis. You have learned to calculate the total capacitance of the 2 capacitors in parallel. You simply add their values together. For capacitors in series, there are 2 formulas available. Notice the similarity between these formulas and those used for resistors in parallel. This brings us to the end of the lesson in alternating current. You have received a large amount